So it's very important to approach each thermodynamics problem with energy in mind. So, by the first law of thermodynamics, the change in the energy of the system is the heat we put in versus the work we get back out. Work can become heat. You can put work into a system and raise the energy in the system, resulting in heat. Heat can become work. You have expansion of gases that move a turbine and give you useful output. And they can both change the energy in the system, depending on how much is put in or taken out respectively. So it's important to also remember what work energy is, and it's the cumulative effect of forces over distance. Right? Basic equation, which you might remember from Physics 101 or a comparable course at a university, is the integral of force times the derivative of x, or the incremental change in x. Do some unit multiplication throwing area in there, that fraction cancels out, the 1 over a and the a, but let's keep it in there and do some unit conversion even further. Force over area is pressure, distance times area, or technically that should be a cross product, not a dot product, but let's not get technical about that. The distance times the area will give us volume, and so the work in our system is the pressure times the change in volume. Or perhaps it's the change in pressure times the volume. Whatever it may be, it's an integral function. Both of them can theoretically change, and so we don't really have to worry about it too much. So work energy, you can think of it as physical energy typically. You can think of it as the energy stored in a spring, the energy stored by keeping something high up, right? Gravity is a force that is constantly trying to pull things down. So you can put something up high, for example, water for a hydroelectric power plant, and you let the energy it accumulates, the work of gravitational forces pulling it down to run some sort of turbine and generate electricity. You have kinetic energy, and that can include friction and air resistance, but on impact, you can actually heat materials, which is where the famous question comes from. If physical energy can become thermal energy, how hard do you have to punch a chicken to cook it? That may sound like a joke question, but it's an actual, genuine question, and someone found the answer for it. Granted, to cook it in one punch, you'd basically blow it up. But it's interesting to think about. And we throw electrical energy in here because we can turn that into work energy in a mechanical form through something like an electric motor. Or we could use something like resistive heating, simply run electricity through a resistor and it heats up, and it can convert that energy directly into heat. So it's important to understand what a system is. And a system, we define it in terms of the mass that participates in a set of processes. So a control volume is what contains that mass. Now you can think of it like the sort of black box analogy. From the outside, without using thermodynamics, we're simply saying we put something into this black box and we get this output. I put this much fuel in and it does this much work. The system is what's inside the black box, and the control volume is the surface, the outside of that black box. And inside of that, with the system, is the device that causes some kind of change to the system. So if you're putting work energy in, that's perhaps a turbine on a shaft, or if you're extracting energy out, that's the turbine taking work energy out of your fluid. And outside that control volume is the surrounding, right? That's outside the black box. So there's three types of systems we have. Open systems, where things can flow into and out of the system, and thus leave with different energy than they entered with. You could have a closed system where the mass of the system is contained, and you end up, once you get back to the start, with the same energy state of your system mass once you've reached a steady state. There can be some complications to that, but for the most time, we'll presume a steady state. An isolated system can be used for experiments like bomb calorimetry because it resists the changes in thermal energy. It resists the flow of energy going in or out. A perfect isolated system lets no energy in or out and lets no mass in or out. Now, aside from experiments, there's an example of an isolated system that you've probably used, especially if you put hot or cold liquids in a thermos. So isolated systems, they usually don't have a cycle. There may be one process in the case of bomb calorimetry. You react a chemical and you get thermal energy out, or maybe it swallows up thermal energy and you measure a change in temperature. But that's about it. It's one process, one direction, does one thing. Or with the thermos example, heat goes nowhere, work goes nowhere, mass goes nowhere, and so nothing happens. But open and closed systems do have processes, and they do have their own corresponding cycles.